Alright, so let us now start moving charges and magnetism, the revision of moving charges and magnetism. And the first points which we will state here, the time invariance of magnetic field. Okay, so this basically means we will assume, that magnetic field may vary with space. Okay, may vary with space, but will never vary in time. This is an assumption that we made. Okay, will never vary in time. Okay, so whenever such a thing happens, that it never varies in time, we call it steady. What do we call it? We call it steady. Okay, and at the beginning of our third chapter, we said, what did we say? Okay, we said that the currents that we're going to discuss will be steady. So if currents do not change with time, we can say so are the magnetic fields produced by them. That is called as time invariance of magnetic field. Okay. आता आपल्याला मॅथमॅटिक्स मध्ये काय शिकलोय आपण, द रेट ॲट विच वन क्वांटिटी चेंजेस विथ अदर क्वांटिटी इज डिटर्मिन्ड बाय इट्स डेरिवेटिव. करेक्ट. So we can say that magnetic field, it appears to us right now, that it depends on the position x as well as time t. Okay, so when a quantity depends on more than two variables or more than one variable, we define partial derivatives. Okay, so the symbol is this. Okay, for ordinary derivatives we just say this dB by dt equal to 0, but in this case we know that it may vary with space, so we just say partial derivative of p with respect to time is always 0 for our case, but this is not 0. Partial derivative of b with respect to x is not 0. Okay, and if our magnetic field is also space invariant, what do we call it? We call it uniform magnetic field. Got that? So there are two things with respect to which the magnetic field can change. In this chapter, we have assumed permanently that magnetic fields never change with time, so we call them steady fields. But we know that they may change with space. Okay, for example, if you go away from current carrying conductor, the magnetic field's magnitude will decrease. So it changes with space. So this is what we have in this chapter. Okay, we are allowing magnetic field to change with space, but we are not allowing magnetic field to change with time, because field has two independent parameters. Okay, the space and the time. We define partial derivatives. Okay, that's one thing. And if the magnetic field neither changes with space nor does it change with time, then we call it uniform. Okay, it's constant everywhere. Okay, so its derivative is here. Okay, number 2, dot and cross notation. What does that represent? A dot drawn on paper. Okay, a dot drawn on the paper tells us that the magnetic field's direction is towards us, normal to plane of paper. Okay, normal to plane of paper or screen. In my case it is screen. If you write it on your paper, then it will be the paper. And what about this? It will be away from us. And we have seen that this dot cross notation not only applies to magnetic fields, but it also applies to the direction of current. Okay, so with that we can start revising this chapter. The first mathematical expression that we encounter is what we call Lorentz force. Okay, now the more general representation of Lorentz force has two components. Okay, and those two components are the Lorentz force due to electric field plus Lorentz force due to magnetic field. Okay, Lorentz force due to electric field and Lorentz force due to magnetic field. Okay, Now, this part for this chapter, except for cyclotron, will always be 0. Okay, usually, because we are not studying electric fields in this chapter anymore. We have already discussed them in the previous chapters. Okay, so then a charge can experience a magnetic field. Okay, as in this chapter, a charge can experience magnetic field only if it has a non-zero velocity. Okay, and the magnitude of the Lorentz force is given by q v bar cross v bar. Okay, this is the force on a charge. And in fact, this expression here allows us to define how strong is 1 unit of magnetic field. Okay, 1 unit of electric field is a Newton per coulomb. Okay, and similarly we can define the SI unit of magnetic field. Okay, and it is Tesla. Alright, if I want to determine the direction of this force, okay, suppose there is a positive charge. Okay, it is moving in this plane with velocity v bar, and in this plane also exists a magnetic field. Okay, assume that it is uniform now, it doesn't change with space or time. Then the direction of the Lorentz force can be determined by this right hand screw rule. Okay, you know that very well, how to determine it. Alright, so please note that this is a positive charge. Okay, this is a positive charge, and if you draw a 3D figure here in which the magnetic field lines are like these, then for positive charge moving with a constant velocity, we know that it will start moving in a circle. Okay, it will start moving in a circle, and in this case, when you look at it from this direction, the tracing of the curve will be clockwise. Okay, and in this case, it will be anti-clockwise. Okay, well, it's opposite. It's basically opposite because of what? Because of the value of the charge being positive and negative. Okay, so this is Lorentz force. ह्याच्यात काय doubt आहे? Okay, yes, I would like to add few more points here. Let me see if there is a separate point that I have made for definition of a magnetic field. Okay, no, it's not. Okay, so I'll define it right here. So we consider a 1 coulomb charge. Okay, suppose we consider a charge of 1 coulomb. Okay, and it is moving with a speed of 1 meter per second. Okay, and its direction is such that the velocity is perpendicular to p bar. Okay, and suppose the force F bar, the magnitude of the force is 1 Newton. Okay, suppose the magnitude of the force is 1 Newton, then the magnetic field is said to be of intensity 1 Tesla. Okay, so SI unit of magnetic field is Tesla. Alright, and the CGS or non-SI unit is Gauss. So 1 Gauss is 10 raised to negative 4 Tesla. Okay, this is the non-SI unit of magnetic field. Okay, fine. So we have defined how strong is 1 Tesla. Alright. The next is magnetic force on a current carrying conductor. Now, this current carrying conductor is also going to produce its own magnetic field, but we are not concerned with that. Okay, we are not specifying what has produced that uniform magnetic field shown in the blue color in the direction away from us towards the screen. We are not stating the source of that magnetic field. We are just saying if we keep a current carrying conductor like this, okay, inside this uniform magnetic field in the direction shown, then what will the magnetic force be? The vector notation tells us that the magnetic force or Lorentz force will be I L bar cross B bar. Okay, I L bar cross B bar, and the direction of the force, the direction of the Lorentz force is given by left hand rule. Okay, the direction of the magnetic force is given by the left hand rule. Okay, so let's do it now. Take the first three fingers, the thumb, the middle finger and the index finger. Let the middle finger point towards the current, so from left to right. Let the magnetic field, that's the index finger, point towards the screen, and therefore the thumb will point vertically upwards. So this conductor, okay, this conductor will be lifted vertically upwards in the plane. So this will be the direction of Lorentz force. Is that clear? Okay. Now in some cases, the the conductor is not straight. Okay, so if it is a curved conductor, in that case we have to integrate this expression. So the elementary length dl bar is now taken, and this is for, and we are supposed to integrate this over the length. Okay. Whatever length of the conductor is inside the magnetic field, we have to perform this integration, and because the angle between the magnetic field and the current element is going to change, we have to be careful. Okay, and well, that's the reason, rather that's the reason why we integrate. Okay, otherwise there's no need to integrate. Okay, that's magnetic force on a current carrying conductor. And then let us analyze the motion of a point charge in a magnetic field. Again, let's look at this figure where the magnetic field is directed away from us towards the screen. It is uniform, and a charge moving with velocity v bar perpendicular to b bar with no acceleration. Initially there is no acceleration for the charge, but has a velocity v bar, and it enters this field. Okay, it is going to enter this field with its velocity being perpendicular to b. Okay, what will happen? The charge will start following a circular trajectory. It will follow uniform circular motion. Okay, it will follow uniform circular motion. So in uniform circular motion, the speed remains constant, but because the direction of velocity is different everywhere, it possesses an acceleration. And what acceleration do we call it? We call it centripetal acceleration. Okay, we call it centripetal acceleration. So this acceleration does not change the speed of the particle, but what does it change? It only changes the direction. Alright, now there also is an associated force. We call it centripetal force. In this case, that centripetal force, mv squared by r, is provided by what? Is provided by the Lorentz force. So that's QEB. Okay, where r is the radius, b is the magnetic field, m is the mass of the charged particle, q is the charge on it, yes, and r is the radius. Okay, and there also is another relationship which you might have studied in your 11th physics, that is v equal to r omega, where omega is the angular speed measured in radians per second. Okay, so by eliminating v, okay, in this case you'll find that r also gets eliminated because v by r is omega, and then additional v is there, that is cancelled by this, and then you get a relationship between the angular speed of the particle, and surprisingly, or rather not surprisingly, it is independent of the radius as well as the initial speed of the particle. Okay, so by knowing the angular velocity of the particle and the strength of the magnetic field, you can actually measure the charge to mass ratio of the particle. Okay, charge to mass ratio of the particle. And more importantly, if we could determine either charge or mass indirectly or by some other method, okay, sorry, not indirectly, by some other method, by plugging in that value here in the charge to mass ratio, which we have determined from this analysis, we can determine the other quantity. Okay, it will generally be mass. Okay, because mass is something that we cannot measure. Okay, because these charged particles, they are extremely lightweight, right? They are extremely lightweight. Okay, so this is the working of this, or rather the mathematics behind the circular motion of a charge in a uniform magnetic field. And and if the velocity is not perpendicular to magnetic field. If the velocity is not perpendicular to magnetic field, then in addition to the circular motion, the particle's velocity always has a component along the magnetic field, isn't it? So let us resolve V bar into the perpendicular component and the parallel component. Okay, so this component is responsible for circular motion. Okay, this is responsible for circular motion and this is responsible for rectilinear motion. Okay, this is responsible for rectilinear motion. It means this part, the V parallel, makes an angle of 180 degrees or theta with magnetic field, which means sine theta will be 0. So Lorent's force contribution of this component of velocity is 0. Okay, is that clear?
तो जो परपेंडिकुलर है V परपेंडिकुलर तो टैंजेंशियल है ना त्या याला
नहीं, it's not. नहीं. Tangential is velocity. Velocity is always tangential. This is okay. See, okay, yeah, a good point. Point one. Velocity is always perpendicular to trajectory. Always. ALWAYS. It is always perpendicular to. Oh, sorry. Tangential. Sorry. It is always tangential to trajectory. Wait. Velocity is always along tangent. No matter what curve the motion is along. Yeah, okay, I'm coming to that. Okay, so this is the first point. If it is rectilinear motion, there is no problem. If it is circular motion, then velocity will be tangential. But even for Earth's motion around Sun, which we consider to be an elliptic motion or motion around an ellipse, along an ellipse, it is still tangential to the trajectory. Okay, so even if the motion were, let's say, around along a parabola, it will still be tangential. Okay, so this component here, this one, is always tangential to that helical path. Is that clear? But at any point or at any instant in time, we can resolve this velocity component along two directions, mutually perpendicular. First, along V bar, which you can see here, V parallel, it is along this thin blue line, which is a magnetic field line. So okay, that is very clear, and this is perpendicular to that. Okay, V perpendicular is not perpendicular to well, not tangential to this, but it is actually perpendicular to magnetic field. It's not tangential to the trajectory. Tangential to trajectory is the original the main velocity. Okay, fine. V parallel is along B bar and V perpendicular is perpendicular to B bar. Clear? Now, because when our particle is going to complete a circle in a hypothetical case where V parallel is 0, okay, during that time in the actual case, it gets an opportunity to travel in the direction of magnetic field if it is a positively charged particle by how much amount? By an amount which is given by, which is called as pitch. Okay, and we have to use the formula distance traveled is speed into time. Distance traveled is speed into time. And how are we going to calculate the time? To calculate the time, we have this expression for omega, qb by m. So if omega is qb by m, the period will be 2 pi by omega. You know that. So what will be 2 pi by omega? It will be 2 pi m upon qb. So here it will be V parallel into 2 pi m upon q. That is known as pitch of this curve. Okay, and that the name of the curve is helix. The name of this curve is helix. Is that clear? Okay. We will not discuss velocity selector and cyclotron because they have been omitted from your syllabus in this course, in this year at least, right? Okay. Next, Biodesert Law. Next is Biodesert Law. Some few important points before we go to the mathematical expression for Biodesert Law. Point 1. This law is analogous to Coulomb's law, whereas the other law of magnetism that we will see later, that is Ampere's law, it is analogous to Gauss law. Okay, so this is analogous to Coulomb's law. Number 2, it shows inverse square nature partly. It depends on how you present it. Okay, shows inverse square nature, and it takes a current element. Okay, it takes a current element as something which is responsible for creation of magnetic field. Creation of magnetic field. Okay, so when I say a current element, I'm fundamentally differing from charge, because by current I actually mean movement. Okay, I'm referring to movement of charge. Okay, that's correct. And that's why the name of the chapter is Moving Charges and Magnetism. So moving charges have two characteristics. They will respond to external magnetic field through Lorent's force, but at the same time they will also create their own magnetic field. And Biodesert law is for that. How to determine magnetic field at a point near a current carrying conductor. Okay. Well, so this quite often we represent it as RDS bar or RDL bar. Because the currents are steady in this case, currents don't change with time, so will the magnetic fields. Okay, they will also not be changing with time. Okay. So this current element is responsible for creation of magnetic field, and now we can go to mathematical expression for Biodesert law. Point 4. Okay, so we have this current carrying conductor, which is a curved one. Okay, it can take any random shape, but we will assume that it is smooth. Okay. Next, now because the distances of a particular point from every current element here are different, we must follow integration, right? So as a representative of the current elements, we are showing this red colored current element, okay, of length ds. So the current element will be IDL bar. Okay, its representation will be IDL bar or IDS bar, in this case a blue arrow. Okay, then I will join this current element with our location. Okay, so this vector is originating here and it is terminating here. That vector is our r bar. Okay, this vector ds to p or dsp is our vector r bar, and the pink vector that you see here is the unit vector in that direction. So if I say that the distance is r, then I will need unit vector. So that is r bar. Okay, and you can determine the direction here dB bar without determining the magnitude of the magnetic field. And to do that, I would like you to imagine this. Take your right hand, wrap your fingers around the wire at ds such that the thumb is pointing upwards in the direction of IIDS bar. Okay, then you'll find that the curled fingers, they're actually coming out of the page from left, and they're entering into the page towards the right side of the wire. So that basically tells you that you must draw a cross here. So dB bar is into page. Okay? Yeah, into the page or into the screen. And the mathematical expression for this magnetic field is mu naught by 4 pi IDS bar cross r bar upon r cube, but we can also write it as follows. dB bar is equal to mu naught upon 4 pi dB bar cross IDS bar cross r cap upon r square. Okay, so what did we do there? Instead of r bar, we just wrote the unit vector in that direction, and because unit vector is changing everywhere and so is ds bar, the direction of ds bar, okay, we have to perform the integration to find the net magnetic field at P due to every current element, okay, for of this conductor. If you need any help in the determination of the expression, first of all I will state the proportionality relationship between magnet element. See, now why are we taking dB bar here and why are we not writing B bar? Because we are not considering the net magnetic field at P. We are considering the magnetic field at P produced by only this current element. Clear? So this is not net magnetic field. Okay. So what does Biodesert Law tell us? Okay, it is an empirical law derived from experiments. This magnetic field here is directly proportional to the cross product of current element and the unit vector in the direction of the point, towards the point, okay, and it is inversely proportional to the square of the distance between them. Is that clear? म्हणजे ते मॅग्नेटिक फील्ड डिटरमाइन करण्यासाठी आपल्याला एकूण 3 गोष्टी लागणार आहेत. त्यातल्या 2 गोष्टी या व्हेक्टर आहेत आणि एक गोष्ट स्केलर आहे. तर ती स्केलर गोष्ट कुठली आहे, तर त्या तो पॉइंट आपल्या करंट एलिमेंट पासून किती लांब आहे ही ती स्केलर गोष्ट आहे. बरोबर. 2 व्हेक्टर्स पैकी पहिली गोष्ट आहे की आपण जी एलिमेंटरी लेंथ घेतोय, ओके, ती त्याला टँजंट कुठे आहे त्या डायरेक्शन मध्ये तो व्हेक्टर असेल, त्याचं मॅग्निट्यूड असेल IDS किंवा IDL, जे काही घ्यायचं आहे. म्हणजे ही जी लाईन काढली आहे ना इथे, ही टँजंट लाईन आहे. दिस इज टँजेंशियल and the current element is always taken along the tangent, just like velocity is always tangential to the path. Literally the drift speeds we can say are tangential to the path. Okay. Yes. The second vector is the unit vector or the vector of magnitude 1 in the direction towards the point where we want to determine the magnetic field. Okay. Now when the proportionality is replaced by equality, a constant of proportionality gets introduced and we take it as mu naught upon 4 pi. Okay. And the value of mu naught is easier to remember. It is 4 pi into 10 raised to negative 7 Tesla meter per ampere. I think you can easily work out the SI unit of this. This is Tesla, so meter cube upon ampere meter squared. Okay. Yeah, so hence it is Tesla meter per ampere. Okay. आता क्लियर आहे?
IDS हा करंट आहे की फक्त
नो इट ओके. करंट एलिमेंट म्हणजे त्याच्यात करंट पण असतो आणि कंडक्टरचा याची एक लेंथ पण असते. इट्स नॉट अ पॉइंट. इट्स नॉट अ पॉइंट.
नाही. सो IDS म्हणजे मी फक्त करंटची व्हॅल्यू टाकायची की करंट आणि कुठली तरी लेंथ? करंट आणि कुठली तरी लेंथ. म्हणजे 1 एम्पियर ओव्हर 2 सेंटीमीटर असं.
येस.
So it's I into ds.
Yeah, that is scalar multiplication, multiplying a vector by a scalar, just like ma bar is force. तसं.
So तसा IDS.
तसं एक्झॅक्टली करंट, म्हणूनच करंट एलिमेंट म्हणतोय ना आपण. नुसत्या करंट मध्ये DI म्हणालो असतो आपण. राईट. या ओके. म्हणजे बेसिकली काय, तर सपोज इथून इथे आपला कंडक्टर आहे, इथून इथे सपोज, याच्यामुळेच आपण कॅल्क्युलेट करतोय मॅग्नेटिक फील्ड. ओके. तर मी काय करेन, मी असं इमॅजिन करेन की मी ह्याचे तुकडे करतोय आणि त्या प्रत्येक तुकड्यामुळे क्रिएट होणार मॅग्नेटिक फील्ड मी काढेन पिला आणि ते ऍड करेन. ठीक आहे. म्हणजे मला त्याचं एक्सप्रेशन मिळेल इथलं. त्याच्यात आता अजून एक व्हेरिएबल असेल आणि ते व्हेरिएबल म्हणजे मी या कंडक्टरचे किती तुकडे केलेत त्याच्यावर. आता जेव्हा मी या कंडक्टरचे तुकडे इन्फिनिटीला टेंड करेन, n टेंड्स टू इन्फिनिटी, तेव्हा मला जी सम मिळेल ना, ते ऍक्च्युअल मॅग्नेटिक फील्ड असेल पीचं. आणि त्यालाच इंटिग्रेशन म्हणतात. वी हॅव डन दॅट इन डेफिनेट इंटिग्रल्स. बट या So this is differential form. You can state it in the integral form as well. Okay, fine. That's Biodesert Law. Okay. So epsilon naught is the permittivity of free space. Alright, and mu naught is called as permeability of free space. We know the association of epsilon naught with Gauss law and Coulomb's law, right? The reciprocal of permittivity is the proportionality constant in the Gauss law of electrostatics, right?
Oh.
Yeah, integral E bar dot ds bar, or dA bar I would say, is equal to Q enclosed upon epsilon. Okay, and now we will see that in Ampere's law the constant of proportionality is mu naught. Okay, now it so happens that if we take epsilon naught and mu naught, the product, okay, we may write it as follows. One upon 4 pi epsilon naught is how much? 9 into 10 raised to 9. So 4 pi epsilon naught will be 1 upon 9 into 10 raised to 9. Mu naught upon 4 pi is already there, 4 pi into 10 raised to negative 7. That's mu naught, so mu naught upon 4 pi will simply be 10 raised to negative 7. So this is 1 upon 9 into 10 raised to 16, which is 1 upon square of 3 into 10 raised to 8. That is 1 upon square of speed of light in vacuum, or speed of electromagnetic wave in vacuum. So we can say that C is equal to 1 upon root of mu naught epsilon naught. Okay? Having seen the speed of speed of electromagnetic waves in that chapter, we can now connect three quantities: the speed of light, universal constant, epsilon naught, and mu naught. Okay? Yeah. Acha. So then we saw the first application. Okay, then we saw the first application of Biodesert law, in which we had a current carrying circular loop, okay, which carried a current I. This loop was kept in the y-OZ plane with origin being the center, and we wished to calculate the magnetic field at some point P on its axis, okay, on the axis of the loop. Magnetic field on axis of a current carrying circular loop. Okay, now because it is a circular loop and we are on its axis, we can exploit the symmetry. Okay, so we have done that in the regular lectures, the theory lectures, so I will not revisit the derivation, but I will just tell you the final expression of the magnetic field which we have at P. Okay, so the magnetic field at P, it so turns out that the magnetic field at P is axial. Okay, it will be along its axis, although the elementary magnetic fields at P created by every current element or any current element, the individual fields are not axial. They will have a component not along the x-axis, but due to symmetry we can always say that for this dBy there will always be another current element here which will be cancelling this magnetic field out. Okay, so the net magnetic field is the actual magnetic field, and its value is calculated as B bar is equal to mu naught I a squared upon 2 times x squared plus a squared raised to 3 by 2. Note that in this case you have the square of the radius, so we can bring the pi term there and get the area of this loop. Okay, and that's how we define magnetic moment of this loop. Alright, and I cap. See, this I cap refers to the unit vector along positive x, and this red I refers to the current that is flowing through this particular circular loop. Clear? A is the radius of the loop. A is the radius of the loop, and I is the current flowing through the loop. Is that clear? Okay. Now I'd like to tell you 3 points here. Okay, three points. Point number one. If x is 0, then P goes to O. Correct? If x is 0, then P goes to O, and then what is the magnetic field there? Magnetic field there will be mu naught I A squared divided by x is 0, so 2 a squared raised to 3 by 2 or 2a cubed I cap, or it will be mu naught I upon 2a I cap. Is that clear? Number two. If x is much greater than a, then x squared plus a squared can be approximated to x squared only. Okay? If x squared plus if x is much greater than a, then the square of that will be further greater than a squared. So we can approximate like this, and then in such a case we get b bar as mu naught I a squared divided by 2x cubed I cap. Now this is an approximate field, okay? This is an approximate field, not an exact field. Is that clear? Now if I divide and multiply by 2 pi, okay? If I multiply and divide by 2 pi, I will get mu naught upon 4 pi here because of this 2, okay? And then I will get 2 pi a squared I upon x cube I cap. The quantity pi a squared into I, the quantity pi a squared into I, what do we call it? We call it the magnetic moment of the loop. We call it the magnetic moment. And we absorb this vector I cap here and we make the magnetic moment a vector quantity. Alright?
Say P bar, no?
No, P bar is electric dipole.
Ampere,
yes, yes. Point 3.
P bar क्या है?
P bar is electric dipole moment. ते पहिल्या chapter मध्ये. Okay, fine. Third point. Actually, based on the second point, if we take a solenoid, okay, and suppose the length of the solenoid, okay, see, that means the radius of the loop of the solenoid is already smaller, but if we now say that the length of the solenoid is also very small compared to the axial distances, okay, then we can actually determine the magnetic field, okay, by maintaining the same expression without disturbing it. The only difference is now nothing will change actually, okay, nothing will change, but using the same formula n times, so we imagine a solenoid being kept here instead of a single loop. If we imagine a solenoid, we know the formula mu naught Ni, and we can modify that also, and on modification we can obtain an equivalent bar magnet, or rather an equivalent solenoid for a bar magnet. Okay, we can adjust I and measure magnetic moment of a bar magnet. Okay, we will do this again in the next chapter, that is magnetism and matter, but the main formula is this is the same formula. Okay, clear? Because our definition of magnetic moment is in terms of the current and area, but a bar magnet has none of them. It neither has current flowing through it, it neither has, well, it may have an area, or it can have area, but it definitely doesn't have the current. So then how can we define magnetic moment of a bar magnet? Okay, in some books we introduce an analogous concept called pole strength, like charge into length of dipole is electric dipole moment. So pole strength into length of the bar magnet as magnetic moment. Can do that. In state board textbooks you will find that, but in your book NCERT it doesn't have. They don't mention that. Okay, we use pole strength, so we will stick to this definition of bar magnets magnetic moment. Okay, clear? Okay, fine. So see, so the development is we know Biodesert law, we apply it here, we get this formula, and then from that we get multiple sub formulae if you want to call them. Okay, fine. Now what about the direction? To determine the direction of magnetic fields due to current carrying loop, we can refer to this figure. Please note that if we imagine this to be in an xy plane, okay, in the xy plane, with this to be the origin, and then the direction of the magnetic field is perpendicular to that everywhere. Okay, so this is along the z-axis. The thumb, if the curled fingers denote the flow of current, then the thumb will point to the direction, in the direction of the magnetic field. Okay, and you also have the other lines here. Okay, so field lines, magnetic field lines, always form a closed loop. Magnetic field lines never terminate anywhere. And also they never originate anywhere. Okay, this is important distinction between magnetic field lines and electric field lines, because electric field lines, they always originate at positive point charges and they always terminate at negative point charges, you know that. But that's not the case with magnetic field lines. So either they will be closed loops like this, or they will be straight lines. Just like Biodesert law was analogous to Coulomb's law, this is analogous to Gauss law. Although there is a separate Gauss law of magnetism, I want you to refer to Gauss law in electrostatics. Okay, so I'll mention it here. Ampere Circuit Law is analogous to Gauss law of electrostatics. Okay, analogous to Gauss law of electrostatics, but there is a difference. The difference is in Gauss law, we need a closed surface. Okay, then although it's analogous, in Gauss law we need a closed surface. In Ampere's law, what do we need? We need a closed loop. We need a closed loop. Okay, and this loop need not be made up of some wire or something. Okay, it can be an imaginary loop. Rather, in most of the cases it is an imaginary. Okay, so what does Ampere Circuit Law tell us? Ampere Circuit Law tells us that if we take a closed loop, okay, if we take a closed loop, not passing through any of the conductors, so if we take this closed loop randomly shown here, and if we decide the direction of integration, okay, if we decide the direction of integration like this, the anticlockwise direction, and if we sum the dot products of magnetic field at all points here with the lengths, okay, so what you have to do is, like I said, how to integrate in the case of Biodesert law, you imagine your Ampere loop or Amperean loop, you may call it, being split into n segments like this. So you pick any one point from that segment, okay, you calculate the magnetic field there, assuming that you know it, or in case if you don't know it, then you just calculate the you take the magnetic field, keep it as an unknown quantity, okay, sum all these things up, take the limit as n tends to infinity, where n is the number of segments that you have formed, you will get the line integral. Okay, the circle on the symbol of integral conveys that the loop is a closed loop, or the curve that you are taking is a loop, it's closed curve. Okay, fine. What next? Ampere Circuit Law tells you that the line integral of the magnetic field, so this in this case ds bar is the elemental length, okay, it's not area, it is proportional to the current enclosed. Gauss law would tell you this: surface integral of electric field, surface integral of electric field is equal to the charge enclosed by the surface divided by epsilon naught. In this case, the line integral of magnetic field taken around a closed loop called Amperian loop, there we called it Gaussian surface, Amperian loop is equal to mu naught into current enclosed. Now, what is meant by current enclosed? By current enclosed, we mean how many currents, what is the net current that is passing in a plane in which your Amperian loop is present. Okay, through the plane. So suppose there are three currents, I1, I2 and I3. I1 is represented by a dot. Dot means it is coming towards us from the plane of paper. I2 and okay, and same thing with I3. But what about I2? I2 is going or entering the plane of the paper. So it is going away from us. Okay. So we have to now algebraically add these currents, but we will not consider I3 because it lies outside. ENC corresponds to enclosed. Okay. Now which of these currents should be taken as positive and which one of them should be negative? To do that, we take the right hand.
I1 positive.
Yeah,
right side.
Yeah, we take our right hand. The fingers except the thumb. They let they point in the direction of the integration. Okay. The thumb will then point the direction of those currents which are considered to be positive. Okay. This is how to assign to the current used in Ampere. Is that clear? Okay. Please note that it is enclosed. It's not the net current, it's just enclosed. Just like this. Okay. This is Ampere Circuit Law. Next is magnetic field due to a solenoid. Okay, next is magnetic field due to a solenoid. So you can think of a solenoid to be made of many current carrying loops, not necessarily circular, but generally solenoid has circular loops. Okay, many circular loops arranged very close to each other. Okay, very close to each other. Okay. Now in our ideal solenoid, we assume that magnetic field inside is is uniform. Okay, is uniform. The lines are parallel. This is the actual diagram zoomed out. So I have separated the adjacent loops of the adjacent turns of the solenoid, but yes, you can ignore that part. You can ignore the magnetic field near this. Okay, the direction. Well, you can argue like this: if the solenoid is very close, the turns of the solenoid are very close to each other, then the superposition principle cancels the field that exists in between the conductors. This is up, this is down, so the effect will be zero. Okay, the field outside is very weak, we can ignore it, and the field inside is uniform and strong, and the expression for that is mu naught and I. Okay, so you have to find and we have to build an Amperian loop here, which is ABCD. Always remember, take a rectangle. Okay, take a rectangular Amperian loop. The portion AB should be inside the solenoid, the portion CD should be outside, and the other two portions will be perpendicular to the solenoid loops. Okay, then BC and DA will not contribute to line integral because the magnetic field and the length DL bar, they are perpendicular to each other, whereas CD will not contribute anything to the magnetic field's line integral because, well, see, not because DL bar is perpendicular to B bar, in fact they are anti-parallel. Okay, so the angle is not 90. But then field there, we have assumed that the field there is 0. Okay, outside field is 0, so therefore only AB portion contributes to the magnetic field. Okay, and well, if we calculate it, it turns out to be mu naught and I. Now where is the length of AB? Okay, why have we not mentioned length of AB? And for that, let me remind you that here n is not the total number of turns. N is the number of turns per unit length. For a toroid, it's the total number of turns, but in this case, it's the number of turns per unit length of the solenoid. okay, also known as turns density, also known as turns density. Okay, so this mu naught is an expression for magnetic field B bar. Okay, okay, it is axial, and it depends on current and number of turns per unit length. Okay, this is one application of Ampere's circuit law. कळालं solenoid?
एडी आणि सीबी का काउंट करत नाही आपण?
कारण इथे जे करंट एलिमेंट्स आहेत ते मॅग्नेटिक फील्डला परपेंडिक्युलर आहेत, त्याच्यामुळे त्यांचा डॉट प्रॉडक्ट 0 होणार आणि लाईन इंटेग्रल मध्ये डॉट प्रॉडक्ट असतो. हा, म्हणजे कॉस थिटा येणार तिकडे. सो फाईन. टोरॉइड नाही आहे तुमच्या सिलेबस मध्ये, राईट? ओके. Let's go to magnetic field due to an infinitely long straight wire. This particular expression can be arrived at by two ways. You can arrive at it either by Ampere's law, which is easier, or by Biodesert law. Okay, both ways give you the same answer. Okay, tedious. Okay, and this is quantitative description. Okay, this is quantitative description of conclusions of Oersted's experiments. Okay, if you remember at the beginning of this chapter, there are three figures shown in the book, right? The iron filings one, and the circle along which, if you keep the magnetic needles, they'll always arrange them themselves in a circle, right? So this is quantitative description of Oersted's experiments conclusion. Okay, so suppose you take a point P, and it doesn't matter where you keep P on this particular line parallel to the conductor, because the conductor itself is infinitely long. So suppose you place it here, and let the perpendicular distance from P and the conductor be R. The magnetic field at this point is mu naught I upon 2 pi R. The direction is given by the right hand curled fingers rule. If the current is pointing upwards, thumb will point upwards, then the curled fingers of your right hand will point towards the magnetic field. So if P were here, then I would have shown a dot here with same mu naught I by 2 pi R value, and in this case it is cross. Okay, the application is very easy of Ampere's law, but I will not do it here. If you want, you can do it, but this 2 pi R expression here is actually the circumference. Okay, it's actually circumference, and exactly, and that's easy because of symmetry. Just like Gauss law and its applications that we have in our syllabus, right? They exploit symmetry. Because Ampere's law is analogous to that, Ampere's law also exploits symmetry. It doesn't mean that Ampere's law is not applicable where symmetry doesn't exist. Yes, it is applicable there also, but then the integral is impossible to find, or very difficult to find. Okay, yes, and well, the point that I was trying to make here is, because no matter where you keep P on this circle, it will always look the same, and therefore we can conclude that the magnetic field there is axial or tangential to the radial direction, or perpendicular to radial direction. Okay. Then by utilizing this expression, we can actually determine the force between two long parallel current carrying wires. A counterintuitive result is that if these wires carry current in the same direction, then the magnetic force between the two is attractive. Okay, same direction, attractive force. Okay, same direction, attractive force. Okay, please remember. So opposite direction, repulsive. Okay, so let these conductors be separated by a distance r, and let them carry currents I1 and I2 respectively in the same direction. Now, because these wires are infinitely long, what we do is we don't talk about the net force, but we talk about force per unit length. Okay, and because of the way the expression is there, you expect interchangeability. That means the same force must be there on I1 due to I2 and also on I2 due to I1 per unit length. So the expression is mu naught upon I1 I2 upon R, and here that mu naught I1 upon 2 pi R is actually the expression that you have got here, okay, due to infinitely long straight wire. Let us just try to determine why is this force attractive. Okay, why is this force attractive? So let us consider I2 and try to determine the force due to I2 on I1. And again, in this case, I will use the cross product thing. F bar is I L bar cross B bar. Okay, F bar is equal to I L bar cross B bar. Now please try to note here that F bar is equal to I L bar cross B bar requires us I1, because we are calculating the force on I1, on the conductor carrying current I1. Okay, so this is I L bar cross B bar due to I2. So I am saying B2 bar. Is that clear? Okay. Now in this case you can say that B bar is perpendicular. So in magnitude F is I1 L B2. But what is B2? B2 is mu naught I upon 2 pi R, where R is the separation distance. So it is mu naught I2 upon 2 pi R, and this expression matches well with this. In fact, that is how it has been derived. Okay, so F upon L is I1 I2 mu naught upon 2 pi. Okay, now let us determine the direction, and for that let us consider the left hand rule. Consider the middle finger, align itself along I1. Okay, now take your right hand. Imagine that you are holding the conductor I2 in your right hand. Okay, and the curled fingers of your right hand will tell us the direction of the magnetic field. Okay, where thumb of your right hand is pointing towards I2. Okay, in the direction of I2. So it will tell you that the magnetic field in which I1 is present will be tangential to the circular magnetic field lines. So now you return to your left hand. You already have the middle finger of your left hand along I1. Now you will rotate your right hand in such a way that the index finger will be in the direction of B bar. And if you do that, the thumb will point downwards. The force will point downwards. Left hand, exactly. Look at this figure here. Okay, so if you do this exercise all by yourself, you'll find that the force will be attractive. Okay, and that force is given by this particular expression. Clear?
How?
Okay, and using this, you can also define 1 ampere. Okay, which is current is the fundamental quantity and not the charge according to the SI units. Okay, so how to define 1 ampere? 1 ampere can be defined as the current that flows through both these wires, which are separated by a distance of 1 meter, where the force per unit length is 2 into 10 raised to negative 7 Newton per meter. Okay, when that happens, then I1 and I2, they both become equal to 1 ampere. Okay, right. So that's how you can define 1 ampere. Get the definition right. So in this chapter, we have definition of magnetic field. How much is 1 Tesla? Again, you have to bring in everything, substitute everything as 1. In this case, we have this mu naught as 4 pi into 10 raised to negative 7. So 4 pi upon 2 pi is 2. So it is 2 into 10 raised to negative 7. I1, I2, 1, 1, R 1 meter. Okay. कळालं ना ते definition of 1 ampere?
How?
Okay. Next, torque on a current carrying loop. This is a simple figure, and this is a more general figure. Now, this is a textbook figure, so I've just included that. The vector notation is the best. The vector notation is the best. Suppose you have a current carrying loop, which is, let's say, carrying a current I, and suppose the area of the loop is A, suppose. Okay, so you define a quantity called magnetic moment. Okay, and this magnetic moment has the same direction as that of the area vector. Okay, the one that you have used in Gauss law. Okay, the vector area. All right. So what is the torque? The torque is m bar cross b bar. The torque is m bar cross b bar. In the scalar notation, it is mb sin theta. In the scalar notation, it is mb sin theta. So never ever forget this formula. Okay, we will also see this formula in the next chapter, next chapter's revision rather, but please never forget this. And if your loop has multiple turns, then m bar becomes NIA, if, wherein is the total number of turns. Clear? So in this figure, that m bar shown here by the bold face, it is actually perpendicular to the plane of ABCD, and b bar is from N to S. Okay. Now, by comparing the expressions, by comparing the expressions of electric dipole, which expressions? Electric fields created by an electric dipole at a point on its axis and at a point on its equatorial plane. We can define magnetic moment of a current carrying loop, which we did already here, m bar is equal to NI bar, but it is due to this analogy. You can see the expressions being resembling each other. 4 pi epsilon naught mu naught upon 4 pi, 2 p electric dipole moment, m magnetic dipole moment, and x. This is for axial electric and magnetic fields, and the second row here is for the equatorial electric and magnetic fields. For the equatorial electric dipole field, it is electric dipole moment upon 4 pi epsilon naught into x cube. For magnetic field due to a current carrying loop, it is mu naught upon 4 pi into m bar upon x cube. Okay, we will see this again, but please note the similarities. That's how we define magnetic moment. Maybe can just remember it that way. Okay, clear? But current into area, okay, that's magnetic moment. Okay, last part. Moving coil galvanometer. What is the function of a galvanometer? The function of a galvanometer is to detect whether there is any current flowing through the coil. Okay, whether there is any current flowing through the coil. Okay, now what is the working principle? The working principle is that if you place any current carrying coil in a magnetic field, it will experience a torque. So it will rotate. And the amount of rotation, the angle through which it rotates, can then be traced back to the value of the current that actually was flowing, and also the direction of the current through the coil. Okay, so what provides the restoring force here, or the restoring torque? The spring, the coil spring, is going to provide the restoring force. So working it out, you eventually arrive at this. The torque due to magnetic field is the torque due to spring. The torque due to magnetic field is mb, where m is NIA, and field is b, and theta is 90, so sin theta is 1. So you can remember it as b now. Magnetic field b, NIA is the magnetic moment. Okay, tau spring is k theta, where k is the spring stiffness. Okay. So this is a coiled spring. It's not, so the SI unit of K is not Newton per meter, it is Newton meter per radian. Okay, fine. So you can connect current and theta. Current is K upon BNA theta, or you can also get theta in terms of current, that's P na upon K. Okay, clear? Now, moving coil galvanometer being an extremely sensitive device, if you want to convert it into an ammeter or a voltmeter, ammeter measures current, voltmeter measures potential difference, not EMF. It measures potential difference between the two, any 2 points in the circuit. So, how to convert a moving coil galvanometer into an ammeter? You attach a shunt resistance. Shunt is a very small resistance. Okay, a very small resistance in parallel with the coil of galvanometer. Okay, so if you attach the shunt resistance here, most of the current will pass through the shunt resistance, it being very small, and only a fraction of that will pass through the coil. Okay, and the deflection will be produced. And you can apply Kirchhoff's laws, junction and the loop, to arrive at this. IFS refers to the full scale deflection. Full scale deflection current. Okay, full scale. And IA refers to the current through the ammeter, and so that is the entering current. IA, the max current, minus IFS full scale into RSH, because RSH into IFS. Okay, sorry, IA minus IFS represents the current flowing through the AB branch through shunt into RSH. Okay, so that is simply the Ohm's law. Sorry, not Ohm's law. Junction loop rule. Okay, so this is IFS. Correct? IFS I minus IFS into RSH. ठीक है, कळालं ना?
IA म्हणजे तो पर्पल वाला,
the incoming current, yes.
Okay.
ठीक है, हाँ. So that is moving coil galvanometer as ammeter. Now, moving coil galvanometer as a voltmeter. Okay, how do we do that? We attach a very large resistance. We don't call it a shunt, but we attach a very large resistance in series with the coil. What is the purpose of that? The purpose of that is to make as small a current possible to flow through this particular galvanometer. Okay, in order not to change the potential difference between the ends the ends A and B, okay, as much. So then, because we want to measure the potential difference across this circuit element, we must connect a voltmeter in parallel to that. In this case, we have to connect it in series. In this case, we have to connect it in parallel, okay, with the circuit element. Alright, now the full scale current, okay, the full scale current, because it is an extremely sensitive device, IFS will be an extremely small value. So to increase the range, we attach this RS. Okay, so RC is the coil resistance and RS is the series resistance that we have attached to the coil. Okay, so this is RS plus RC into IFS. That will give you the range of the voltmeter. Is that clear? Okay. Alright, so that completes the revision of moving charges and magnetism.